Hello, and welcome to Beyond the SQL Where Clause, Isolating Saas Multi-Tenant Data in Shared Relational Databases. My name is Michael Beardsley, and I'm a Partner Solutions Architect with the AWS SaaS Factory. I'd like to start with a bit of an introduction, and then we'll dive into multi-tenant data partitioning options and how they influence your isolation choices. With that background, we can talk about using a feature of PostgreSQL to solve some of these challenges. I'll show you some example code and cover some real-world gotchas. We'll wrap up with things to think about and what resources are available to you as an APN partner. So let's get started. Today we're talking about data, your customer's data, and here I use the term customer and tenant interchangeably. It is critical that one tenant cannot view or gain access in any way to another tenant's data. Gaining your customer's trust is critical to success in business, and it's easy to lose that trust. You don't want to damage your brand or potentially lose any business from some sort of cross-tenant data breach. Let's clarify some definitions. When I say partitioning, I'm referring to the physical or logical separation of one tenant's data from another. Isolation, then, refers to the security constructs used to prevent one tenant from accessing another tenant's partitioned space. So just because you have one tenant's data in a different S3 bucket or database table or Elasticsearch index doesn't actually prevent another tenant from gaining access to it. That's isolation. Isolation is the security component that you put on top of those partitioning structures. We see three main architectural approaches to multi-tenancy. The first, on one end of the spectrum, is what we refer to as a siloed architecture, where each tenant uses a separate set of resources and a separate environment that your application is deployed into for each of your tenants. So complete separation between the tenants. On the other end of the extreme, we have what we call a pooled architecture, which is where all of your tenants are in shared resource constructs. So shared databases, shared application servers, and there's some other mechanism by which you partition and isolate one tenant from another using security policies, access control lists, things like that. And then in the middle, halfway between a silo model and a pool model, we talk about a bridge model where some tenants use separate resources and some use shared resources. Maybe you have larger customers in their own environment, and you've got some of your smaller customers sharing a second environment. Or you might think of bridge as the resource themselves are shared or siloed. So maybe your application server is shared by multiple tenants, but then once you get to your data layer, maybe your databases or your file storage are separate for each tenant underneath that shared application server. So two different ways to think about a bridged architecture. And now that we've sort of defined those three approaches, let's look at them through the lens of data partitioning, and we'll see how those choices then influence isolation. So we'll start with siloed data partitioning. So when you think about data partitioning in a silo model, each tenant is going to be in their own database. So no shared data, everybody's sitting in their own database with their own database connection then for each tenant. So that means for your application to understand how to talk to the database for the given current active user, there's going to have to be some sort of mapping or metadata that you maintain to understand how to connect to each different tenant's database as that tenant flows through your system. And that's what's depicted down here in this flow on the bottom. A tenant comes in, they need data through your application. First, your application has to figure out which connection to use, and then it has to redirect to that particular connection. So a little bit of overhead there, maintaining the mapping between tenant and database. There are some really strong pros to siloed data partitioning. You get really strict isolation because there's no sharing of anything. So you're really isolated at that database connection level. Because every tenant is in their own database, backup and restore of a given tenant's data set, or archiving of it or deleting it if you're in some data sovereignty law situations where you need to be able to remove data if a customer were to leave you, or things like that, that becomes a little bit easier in a siloed model because there's no sharing going on. And because you're not sharing those resources, there's no performance hit from one tenant influencing another tenant's performance. So there's no noisy neighbor problems because you don't have any neighbors. However, there's some downsides to silo. It's certainly the highest cost of all of the options because you have to pay for each of those independent databases. And because you have more resources floating around out there, you have to maintain more of those resources. So you have the highest maintenance cost. And again, because of all of the numbers of resources that you have to manage out there, you also end up with a complicated monitoring situation. You don't really have one view of your entire system, the health of your system. And it impacts your ability to be agile in terms of releasing new features and getting fixes out there and to delight your customers. The DevOps and deployment and DBA functions just becomes that much more critical because there's so many of these copies that you have to deal with. And because they're copies, there is a tendency for you to be able to, it's awfully easy to make a change or an alteration to one tenant's database and not have that reflected in all of your other tenants' databases for even the most casual reasons. Maybe you make a hotfix to make a big customer happy, and you add an index to something that fixes their immediate problem, but you can't really run the risk or the overhead of doing that for all of your hundreds or thousands of customers all right then. So you put it on the backlog, you intend to get back to it, and for whatever reason it slips or it doesn't happen. So there's a chance then that you get drift between your databases. And even worse it would be making a specific schema change, adding a column or changing a data type for one tenant and then not having that the same for everybody else. You also have that extra layer of code that you have to maintain. Like I said, you have to maintain that metadata layer to understand which connection goes with which tenant. And that's just more programming and more code to test and maintain. And you can't really share any of your common data, so you have to copy everything. So if you've got some lookup data or some non-tenant specific data, you can't have that in one place. You have to manage as many copies of that as you have tenants. So then if we look at the bridge model, when we think about data partitioning is usually implemented using namespaces or schema. So here, this drawing depicts a single database. So now you're not in a separate database for every tenant. You just have one database, but each tenant is in its own namespace or its own schema. Most vendors call this schema. MySQL doesn't really, or MariaDB doesn't really have a concept of schema. Here it would be a database. It would be a different MySQL database per tenant. And here you can see that each of your tenants connects to the same database, so same connection string, but they each query against their own named schema. If we look at the pros and the cons of a bridge model, you do now start seeing some cost benefit because you're not having to pay for multiple databases, you're just paying for one. Another big benefit is now you're using a construct in the database engine itself to enforce isolation. So here you're using a built-in logical partitioning construct of a namespace. You're not writing code to do this. And again, you still maintain some of that flexibility that you got with a siloed model in terms of backup and restore. However, you still have really high maintenance costs because each schema, all DDL statements have to be run against each schema independently. You can't just run it against a single cluster or a single database. If you're going to change indexes, or you're going to change columns, or you're going to add things or remove things or change data types, you have to do that sequentially to each of the schema available in a single database. Tenant onboarding can be a little bit complicated when a new tenant comes on board. This is also a downside of Silo in a way, but when a new tenant comes on board, you're going to have to create a schema at runtime hot while all your other tenants are using that database in that running database. So it's in a silo model, when a new tenant comes on and you have to stand up a new database for them, at least you're not impacting all of your other customers while that's happening. Here in this bridge model, you would be doing it in that shared database. Again, there's this opportunity for each of your tenants' schema to drift from one another and have those changes, which impacts maintenance and impacts your ability to be agile with the marketplace. And just like before with Silo, here we also have to maintain some sort of metadata to understand which schema goes with which tenant, and then at runtime, every single one of your SQL statements is going to have the table names be dynamic, because you're going to have to add the namespace in front of the table name for every single query. And again, it's complicated to share common data. It is possible to share common data. Unlike the siloed model, at least it's possible here, but to do that, you would most likely end up putting that shared data in a shared schema, and that then opens up a little hole in your armor, if you will, where some of your SQL statements are hitting a shared schema and some aren't, and then what happens if somebody screws up and puts the wrong schema name into the SQL queries. And then lastly, let's take a look at what data partitioning means in a pooled model. So now in a pooled model, all your tenants are in a shared database, and they're all using the same schema. So here there's a single schema and everybody's data is inside. And instead of using the database itself or the namespace within a database to partition, here we're using some other discriminator, and usually you would see that as some sort of an indexed value in each table that identifies the tenant that that row's data belongs to. So here in our example, we've got a couple of different tenants, and tenant 1 here, you see the GUID in that tenant ID column. And we've highlighted that first column in blue there is the same for those 3 rows. So each of those rows belong to tenant 1. And so to access this data, then you would need to understand in your SQL which rows to look at. So what are the pros and the cons to a pooled model? Well, because you are running a single database with a single schema, you get both the maximum amount of agility for you to move fast and make changes, and you also have the minimum cost because you're only paying for one resource. You have low operational maintenance from a database perspective because, again, you're only maintaining that single resource. And onboarding a new tenant is super easy, very straightforward, because you're not making new schema, you're not making new databases, you're not making anything, you're not making any new resources for your tenants in terms of your data model. But there are some downsides, and there's a reason why, if it's this good, why doesn't everybody do it? Well, because there's a little bit higher risk in terms of what you're exposed to from an isolation perspective. It depends on your developers, on your software engineers, doing the right thing with every SQL statement every time. And that even is even more important in your really complicated SQL queries where you have nested tables, nested joins. Maybe you have correlated subqueries. All of those things have to get those where clauses correct to both isolate from a tenant's perspective as well as the normal search query that's going on in the where clause for whatever business operation you're trying to perform. And we should say that it could have a bit of a runtime impact, a negative runtime impact. Now we've got all of your tenants sharing the same resource. If one tenant is really hitting the system hard, it could negatively influence some of your other tenants. And because everybody's in the same resource, it's possible that you will find that you have to use a larger instance type, for example, with a little bit more memory, maybe some more CPU cycles to be able to handle the load of all of your shared customers in one place. So then the challenge that we're trying to solve here is how can we benefit from the pooled model pros, lower maintenance costs, lower operational costs, better agility, but how can we do it in a secure way that's easy and consistent and dependable? How can we minimize the impact that our software developers have on our security so that we're not relying solely on their actions to enforce isolation, but maybe we can rely on some more fundamental construct of the database engine itself. And so to achieve some of those answers, I want to take a look with you at a feature of Postgres called row-level security. Row-level security, or RLS, is a user-defined security policy, and those policies are applied to a table, and they restrict which rows are returned or which rows are affected by a given query. You add or remove policies from a table with an alter statement, and you define the policy itself and the rules of that policy is going to enforce with a using clause, and all that using clause does is it returns a Boolean, and if the Boolean returns true, then the query has access to that row. If the Boolean returns false, then it is as if that row does not exist. You can have different policies for read than for modifications. So select statements can have one policy, updates, inserts, and deletes can have different policies. And you can have multiple policies applied at any one time to a single table, giving you a lot of flexibility in what your security footprint for that given table could look like. And this feature is available in both Amazon Aurora with the Postgres compatible database engine, as well as the Postgres offering in Amazon RDS. So let's take a look at what an RLS example might look like. So here is some SQL. In the top stanza, I'm creating a super simple table for my tenants. It's got a primary key for my tenant ID. They've got a name. Maybe they've got some other attributes. Here we've got status and tier. And then to use RLS, the first thing I have to do is I have to enable row level security on the table. So I do that. And then once I've enabled row level security, then I can create a policy on a given table. So here I'm going to create a policy. I'm going to give that policy a name, and I'm going to give it a name of tenant isolation policy, and I'm going to apply that policy to my tenant table. And then here's my using clause, and this is the rules that are going to return a Boolean that tells the database engine, tells Postgres whether to consider a given row for a given query. So here I'm saying that I want the tenant ID, the value of the tenant ID column in the table to equal the current user that is logged in to the database. So as the database engine, as the query planner goes through the rows in the table to decide whether to include them or not, for every row, it's going to look at the tenant ID column, and it's going to compare that value to the currently logged in user. And if they match, then that row will be included. And if they don't match, it'll be as if that row doesn't exist. So let's see what this might look like. So here these are just some examples from the command line PSQL client to talk to Postgres. So here, first I'm going to log in as the table owner, or maybe the master user, the root user of the database, who by default, table owners are not restricted by RLS policies, and we'll talk about that in detail a little bit later. So here I am, I'm the admin user for this database, I'm the master level user, and I'm going to select all the records from my tenant table, and you can see here that I've got two different tenants, and they have two different IDs that identify, two primary key IDs that identify them. So now I'm going to log out, and now I'm going to log in as one of those two tenants. So I log in as one of those two tenants, and now my current user name, effectively, my current username is now the GUID, the ID from one of those two tenants that was in the table from tenant 1. And now that I am not the master user or the table owner, now I'm just a normal login user. Now I can see when I try and select from the table, I only get to see the rows that match my identifier. And you'll notice here that there's no errors, there's no messaging from the enforcement of the security policy for this select statement. Rows that it doesn't tell you that you didn't get to see n number of rows that didn't match your policy. It doesn't refer to the policy in any way. Rows that don't match the using statement just simply don't exist in the result set. And even if for some reason you understood what was going on and you were able to, through SQL injection or some sort of hack, explicitly ask for another tenant's data while you're logged in as tenant 1. So here we are explicitly asking for all the rows from our tenant table that are owned by the ID for tenant 2, you'll see that you get 0 rows. And the security policy is going to protect you. Update and delete statements are enforced in a similar way because, again, there's no rows that match. So here, when I say update the tenant table and change the name of tenant 2's row, it won't work. You'll see update is 0 rows affected. And same if I try and delete those rows. So again, I'm logged in as tenant 1, and as tenant 1 login, I try and delete the row for tenant 2, and I don't get to do it. I get 0 affected rows. However, insert statements that fail a security policy will actually throw an error. So here you'll see an error that is printed out. So here, again, I'm logged in as tenant 1. I try and insert a row, and I try and insert that row as tenant 3. And here my ID is being auto-generated for me, so I don't list it in the columns that I want to give a value for. Tenant 1 can't insert a new record because the tenant ID column won't match tenant ID's identity. And here, if we added tenant ID to our column list for our values, and even if we gave it the correct value, even if we gave it tenant 1's ID, the insert will fail because we've set that column as a primary key in our database, and a primary key implies uniqueness, and so it'll throw a unique key violation if we tried to do that. So that's what it looks like from a raw Postgres standpoint. Let's take a look at how this might look implemented in an actual product. And let's start with some real world considerations here. So as I mentioned before, by default, super users, so in Amazon RDS, we call that the master user. And if you just install Postgres on your own, it's usually the Postgres user, unless you change the name of it, or make another user and give them super user privileges. But any super user or master user and any role that is created with the bypass RLS attribute will not be subject to table policies. Also by default, and that's important because the super user needs access to every object in the database engine to be able to appropriately maintain and keep it running. So that makes sense. By default, the table owner will bypass RLS policies unless you issue another alter statement on that table with force row level security. If you set force row level security on that table, then even the table owner will be impacted by RLS policies. Another thing to think about here as you learn more about RLS and as you go and search around the internet and find some examples, if you use the current user keyword that implies the username of the currently logged in principal to the database engine, if you use current user in your using clause, you would have to create a Postgres login role for every single tenant of your system. So if you don't have a really high number of tenants, maybe that's not such a big deal, but if you've got hundreds or thousands or tens of thousands of customers that are different tenants in your system, that might be a little unwieldy. And also to remember that RLS policies are executed before any filtering or aggregations are done by the backend engine, and it does that so that it prevents any security leaks. You don't want some bottom-up aggregation to include rows that it shouldn't, and have that leak data across the boundary of the policy. And because it's looking at everything, and it's looking at it every time for every query before it executes the query, there is a little bit of performance overhead. It's not much, and if you keep your using clauses simple and you don't utilize, nested views or big joins. You don't want to join tables in your policies if you can help it. If you keep the Boolean statement short and sweet, and particularly if you can reference an index column like we did here in our examples, just looking at the primary key of the table, then you're not really going to notice any performance impact on your workloads. So one of the biggest downsides here is this concept of using current user as the thing that you're testing against. So what are your options if you don't want to create a database user for every tenant? Well, another way to approach this is to use what Postgres calls a session variable. And so here you can access the value of a variable using the current setting function. And here we've created a configuration variable named app.currentTenant. It's important that you name this variable with a prefix dot the variable name. So here our prefix is app for application. We have a dot in between, and then current tenant. Any configuration variables that do not start with a prefix, that don't have something with a dot before the name, those have to be entered into the PostgreSQL conf configuration file, and you don't have access to that in Aurora or RDS as a managed service. You don't get to alter that file, so make sure that when you're creating your variable names that you're using that prefix. So great, so we're going to use a runtime config variable, but where does that come from, and where do you define that variable? There's two different ways to declare the value for that variable. You can either use the built-in Postgres function called setConfig, which maps to the set command, which is part of ANSI SQL. So you can either issue a SQL query with the set keyword versus select or update or delete or any of the others, or you can use the setConfig function. What you'll need to do is you'll need to execute one of these two to set the value for this config variable when you create the database connection in your software. And these variables are local to the database connection. So they're private to each connection. They can't be sniffed or looked at by any other connection to the database backend. So they're safe from that regard. So let's take a look at an example implementation. Here I'm showing an example that's using Java database connectivity. This would be very similar in other languages that all have this concept of a connection handle. And normally you would pool your connections in your code, but if you dig into how your database connection pool software works, eventually the pool calls get connection. So here what this is doing is it's overriding the default get connection setting, and it's going ahead and here it's getting the connection to the database. But the very first thing before it hands that connection back to any calling code is that it issues that set command. And here we'll just imagine that there's some sort of a global singleton for tenant context, and if you call get tenant on that object, it'll get you the currently authenticated tenant user or tenant ID of the user that's logged in, and we set that configuration variable for that database connection to that current tenant, and then we give that connection back to the software. So what are some takeaways? Well, we have to start with security. Security is job 0 at Amazon, and it should be job 0 for you too. Make sure that your tenant data is isolated. and that we've minimized to the extent of our abilities any cross-tenant data access. How you choose to partition your data of your tenants affects your choices for isolation. We looked at some of the pros and cons from a siloed, abridged, and a pooled model. Pooled architectures promote agility. Pooled architectures are cost-effective and they're easier to maintain. But we need to move the enforcement of the isolation, move that security burden away from the everyday developer tasks of writing those SQL statements and move it closer to the database engine. And we did that by setting security policies, RLS policies, on the tables themselves when we created the tables with the create syntax, the DDL statements that create the table in the first place. And then the only place that you see any reference to that in our code is deep down in the innards of your database connectivity code. There's one line in there, and that line, that's not going to be touched by your developers every day. Your developers might not even know that line exists in the code base, because none of their SQL statements are going to be changed. They're all going to be protected. They're all going to be protected by the security policies in the engine. We also like to suggest that you use product features when it's available instead of trying to roll your own solution. So if there's a built-in mechanism like Postgres has to secure your data in a shared table, take advantage of it. Don't recreate your wheel. You're going to get all of the performance and security and all the agility that they're providing you as a vendor as they improve the RLS subsystem in Postgres by using what they have versus you having to maintain and test all of that on your own. RLS from Postgres gives you freedom to write really fine-grained isolation models. Again, you can use different policies for reads than you can for writes, and you can apply multiple policies to a table. And we suggest that you also pursue other materials that are available to you. The Saas Factory has a number of blog posts and white papers available to our APM partners. We have self-paced learning modules, webinars such as this one. We have quick starts, and you can work with your account manager or your partner development manager if a one-on-one engagement with a business or solutions architect from the Saas Factory team seems like it could help you on your journey to a SaaS product in AWS. So thank you, and we'll be following with question and answers period after this.